Hello students. This video I'm going to explain further the location of the force, hydrostatic force on plane surface. And in general, let's consider a situation where the plane surface is not symmetric with respect to the vertical axis. So the centroid of the area, and this is the center of pressure, do not lie on this axis here, so that there is this EH supposedly. So remember that the distance between the centroidal axis, this axis here, and this axis here is denoted with E. And if the plane surface is vertical, E is just E sub V. And E, by the formula and in the derivation, it is equal to moment of inertia with respect to the centroidal axis of the area or plane surface, I sub Cg, sine of theta divided by area bar H. Because sine of theta, angle theta is here, and here also is equal to bar H. So that's bar H divided by bar Y. So this would be the one of the complicated cases. So we need to solve or locate center of pressure horizontally. Vertically, all you have to do is solve for that E and apply this formula. But what if horizontally? We will call the length of the line through the center of pressure as L. That is L. And in the derivation, because we consider this strip here and every element or every point on this strip is equidistant from the liquid surface H. So that means the pressure, which is equal to gamma times H, is constant or uniform. So this pressure diagram is rectangular. The differential force over that strip is therefore acting through the centroid of this pressure diagram. And since the pressure diagram is rectangular, it is natural that this dF here passes through the centroid of this rectangular pressure diagram. So if in general the length of this strip is x, which is denoted here x, then dF is acting at half of x, x over 2, x over 2, because this is rectangular pressure diagram. So because of that fact and because of that idea, we conclude therefore that CP is located horizontally after we solve for L at L over 2 from the left or from the right. So the idea is we have to solve for L through the center of pressure. After we solve for E, then half of that L is the location of the center of pressure. So for instance, this is the area which is trapezoidal, and this is the centroid of the trapezoid. And of course, you have to break the trapezoid into two known areas so that it's easy for us to locate the centroid. So we break that into rectangle and triangle. That should be the procedure in order to locate the centroid of the trapezoid. Now, after we solve for E, we have to find the length here, which is denoted with L, and the center of pressure is L over 2 by the principle here. So, for instance, if the upper base of the trapezoidal plane surface is V, and the bottom base is capital B, and the height is H, then the location of the centroid of this triangular part is equal to 2/3 of h, because the centroid of the triangle is 2/3 of h from the vertex, then plus e. That is it. So therefore, because we can only apply similar triangles for this triangle here, so we have this length from here up to here equal to L minus B, where L is the length of that line, then B is the upper base of the trapezoid, because this is also B. So this is just one demonstration. If the area or the plane surface is trapezoidal, so by similar triangles, L minus B, this one, as to this height here, which is 2/3 of h plus e, equals capital B minus B. So of course, this part of the triangle is big B minus small b. So big B minus small b as to h. So from there, we can solve for L. Then knowing L, half of that, we can locate the center of pressure. This is where the line of action of the total pressure or the force F acts or passes through. Now, for the complicated case, by the way, because we have to use force equals pressure at the centroid times area, after we solve for the pressure at the centroid, we equate it to specific weight of liquid in contact with the plane surface. Let us say that liquid is liquid 3 and the specific weight is gamma times 3, then times barred h. So to solve for barred h, because if we encounter a complicated situation, barred h is not the distance from the centroid to the surface exposed to zero pressure, especially if there are layers of fluid. The idea there is we convert all those liquids with a single liquid. Let us say this is now the single liquid at gamma 3, and this is barred H. Remember, if there is only one liquid, the distance, vertical distance from the centroid of that area to the liquid surface is barred H. But if we have layers of fluids, that's not barred H. We still have to compute barred H. And how to compute for barred H? After we compute for the pressure at the centroid, we divide it by the specific weight of the liquid in contact with the plane surface. That's the principle. Now, let's proceed to the question. This is the formula for E. When can the centroid of area and the center of pressure coincide? When you say centroid and center of pressure coincide, that means E is 0. So this value of E is 0. When can E be 0? In other words, so there are three cases. One is when the plane surface is horizontal. That means if the plane surface is horizontal, theta is 0. So when theta is 0 in the formula, sine of 0 is 0. So 0 times something divided by, definitely there's the value here, would be 0. So that's one way, one thing that E is 0. Or when E is 0, then that means CG and CP coincide. So this is the demonstration. When the surface is horizontal, then CG and CP coincide, and it is horizontal. Number 2, when the surface is in contact with gas or air. So remember, for example, this closed chamber here, and this is the plane surface, rectangular plane surface or any plane surface. Remember that when the fluid inside is gas, the pressure is the same. So any point on the confined space, the pressure is the same, pressure of the gas or pressure of the air. So that is rectangular in diagram. So the pressure diagram is rectangular. Therefore, F acts at CG and it also acts at CP. The centroid of this rectangular pressure diagram is also CP. There's no E here. So it is 0 because the pressure diagram is rectangular. The centroid is at half of the height. So that's the second way. And the third way is if you study the formula, BARD H will depend on the position of the plane surface. And this E here will only be 0 even if there is theta when BARD H is very, very high or very large, or BARD H approaches infinity. When that happens, any value divided by BARD H, which is very high, would approach 0. So when the surface is brought to a very deep point, and it means BARD H approaches infinity, then that's another case where E is 0 or where CG and CP coincide. This is just a demonstration, but this is, of course, BARD H here is not approaching infinity. For example, the height of this plane surface is 1 meter, then this will only be 10 meters. 10 meters plus 0.5, 10.5. It's not infinity. But even if it is just 10.5, we notice that if we draw the pressure diagram, this pressure diagram seems to be rectangular. So that means the centroid of the rectangle is also the center of pressure because the force which is passing through the centroid of the rectangular pressure diagram is also the centroid of this rectangular surface. Much more if BARD H is made 10 kilometers, this is only 10.5. If this 10 kilometers, definitely this becomes rectangular in shape. Even if BARD H is just 10.5 meters, it is now almost rectangular in shape. So those are the cases. So we now proceed to continue by solving problems on plane and curved surfaces. By the way, before that, let me discuss first the hydrostatic forces, components of hydrostatic forces on curved surfaces. Now, in this illustration and demonstration, the length of this curved surface perpendicular to the screen is constant. Also, there are curved surfaces perpendicular to the screen. The length is not constant. For example, spherical, perpendicular to the board, it varies from 0 to the diameter. So that's it. Conical, for example, surface. So it's not constant. So in this illustration, the curved surface perpendicular to the board will have constant width, and I will call that width B. So therefore, if we position ourselves here, the projected area or shape of this curved surface, if it is constant with perpendicular to the screen, would be rectangular. So this one. So we draw horizontal line through A and through B. Then the height of the projected surface would be this vertical distance here, the vertical distance between A and B. And it is rectangular in shape if the width perpendicular to the screen is constant. So that is B. This is the height of vertical distance between A and B, HAB. So it is rectangular. So therefore, FH, this is the centroid of the projected area. FH is acting below because there is E or E sub V. And it is specific weight of liquid barred H area. Now, for each location, we have to solve for E sub V or E. And barred H is the distance from the liquid surface to the centroid of the projected area. So that is for FH. Now, how about for FV? So, if we imagine that this is your back side, so that you can feel the force acting on your back side, it is pushing your back downward, right? So, therefore, FV is downward. And since friction cannot develop when the fluid is at rest, so remember, there is a principle that, and it is also shown in the lecture part, in one of the lecture videos in fluid mechanics and hydraulics, that there's no friction when the liquid or when the fluid is at rest. So that's why if we consider this as a body, this volume here, and there's no friction on this side because the fluid is at rest as well as here. So the only force acting would be that FV, and we thought that this FV here is simply the weight of liquid above the curved surface AB that pushes our back. If we imagine that this is our back, so that we can anticipate the value of FV. So FV therefore is the weight of liquid above AB. And what is weight? Weight is specific weight of the liquid times volume. And what is that volume? Volume above AB. And what is that? How do we compute for that volume? Of course, we have to consider this, and that part is rectangular, of course, and this part is area bounded by this curved surface, this vertical line, and that horizontal line. Now, this curved surface may be circular, may be parabolic, or any curve. As long as the equation is provided, we can easily compute for the area here. If it is circular, quarter circle, for example, and it is, this area would be area of square minus area of quarter circle. If it is parabolic, then this may be a spandrel of parabola, this part, parabolic like that. And it is 1/3 of that base, then times height. So don't worry about this. This is just the general shape. If the equation of this curve is given in general, then use calculus in determining that area by integration. So that's the first case. The liquid is above the curved surface. Now, how about for the situation where the liquid is under or below the liquid surface? So the technique is we draw horizontal line through the endpoints in contact with endpoints of the curved surface in contact with the liquid. Then from there, the vertical distance of these horizontal lines would be the height of the projected area on the vertical plane. Then, as I said a while ago, this is only true if the width perpendicular to the screen is constant at B. So the projected area, this time we position ourselves here, would be rectangular. And this height is the vertical distance between A and B. So FH now is going to the left. We still apply gamma barred H area, where barred H is the distance from the liquid surface to that centroid of the projected area. Then FV, this time, is, because this is now the imaginary volume above AB, it is now upward. Of course, if this is our back, we experience that we are buoyed up or pushed upward. So therefore, FV is upward. And that FV, because it is equal to the weight of liquid imaginary liquid or real liquid above curve AB up to the liquid surface. There's no liquid surface here, but we just extend this part. This is an imaginary liquid uh, above AB. And the important thing is FV is upward. And how to solve for FV? It is the same. Specific weight of liquid times volume of liquid above AB. Although there's no liquid, imaginary liquid above AB. So this is the imaginary volume above AB. Therefore, FB passes through the centroid of the volume above AB. And because the volume is this shape here, this area here, and perpendicular to the screen, it is B. The volume is just area, this area here, times B. And of course, we have to divide the area into known areas. Rectangle and this area here. This is known, especially if this is circular or parabolic or with given equation of the curve. So FB passes through that point. That point is the centroid of imaginary volume or centroid of imaginary area if B is constant. So that's why the volume is just this area times B, because the centroid of the area travels by B. So volume is area times B or area times H, remember? Where H is the distance traveled by the centroid of the area. Now, another important thing, if we have here a circular surface, then from calculus, this is the tangent line and the normal line passes through the centroid. That normal line is also the line of action of the resultant force, the resultant of FH and FV. So, considering this case or this case here, if this is circular, the resultant passes through the center of this circular surface or arc. So that's the principle. Therefore, since the moment of the resultant is equal to the sum of the moments of its components by Varignon's theorem, then the moment of F about the center is 0. And that's also the sum of the moments of its components, Fh times moment arm minus Fv times moment arm, considering, or Fv times moment arm minus Fh times moment arm, considering counterclockwise as positive. So if this is the circular surface, this is the resultant, these are the components, that F here, if extended, will pass through the center of that circular arc. So only for circular arc. So that's the principle. So let's have this first example. The cross-section of a freshwater tank with a slanted bottom is shown. A rectangular door 1.6 meter by 0.8. So since this is shown to be 1.6, so perpendicular to the board, it is 0.8 meter. So 1.6 perpendicular to the screen or the board or the slide is 0.8. But the centroid of the rectangular area is from A, we have 0.8, half of 1.6, and from the bottom, it is also 0.8 meter. The force F acts below the centroid of the area at a distance E. Therefore, the moment arm of F from A, where at A we have a hinge, is 0.8 plus E. So in this problem, I presented two ways to solve the problem. So to set up the equation for P, the force that is needed to open the gate, take note that when the gate is about to open, there is no reaction between the bottom of the gate and this part of this chamber. So that's the idea from statics. Of course, when the gate is about to open, there should be no reaction here. So it loses contact. So that's why summation moment A equals 0. P, the moment arm is this. We have a right triangle. The angle here is 30 degrees. And the hypotenuse is 1.6. So therefore, the adjacent side of this right triangle is hypotenuse 1.6 cosine of 30, 1.6 cosine of 30 degrees. Then equals F, the moment arm of F would be E plus 0.8. So our problem is F and E. And what is F? Because there's only one liquid and this is water and it is exposed to the atmosphere. Therefore, we use the formula for F, specific weight of water, barred H area. Where barred H is the distance from the vertical distance from the centroid to the water surface. And since this is 1.2 up to A, then we add this vertical distance, which is we have a right triangle again, the angle is 30, and the hypotenuse is 0.8. So therefore, this is 0.8, this part, additional 0.8 sine 30, and that is 0.4. Barred H, therefore, is 1.2 plus 0.4. So it is 1.6 meters. And the area is the area of the rectangular gate, which is 0.8 meter perpendicular to the screen times 1.6, which is seen here. So 20.09 kilonewtons. We then solve for E, I sub CG sine theta over area barred H, where I sub CG of rectangle is B, height of rectangle cube over 12. Then sine theta, which is 30 degrees, theta is 30 degrees, over area BH times barred H. Therefore, the compact formula for E is height of rectangle square sine theta over 12 barred H. The height of the rectangle is 1.6 square, and sine of 30 degrees over 12 times barred H, which is 1.6. So it is 1 over 15 meter. Substitute here because we already solved for F and E. So P times 1.6 cosine 30 degrees equals 20.09 F times quantity E 1 over 15 plus 0.8. Solving for P, P is 12.57 kilonewtons. Then the other thing is if you don't want to solve for E, but this is only applicable when the area is rectangular. For other cases, you cannot use this alternate solution. So this is the alternate solution. I consider pressure diagram. This is the pressure diagram. The pressure at the upper point A is specific weight of water times vertical distance 1.2. So 9.81 times 1.2. While at the bottom point here, this height is 1.6 meter hypotenuse sine of 30, so 0.8 meter. Therefore, the vertical distance of the bottom point of the gate from the water surface is 1.2 plus 0.8, which is 2 meters. So the pressure at the bottom of the gate is 9.81 times 2. So we have a trapezoidal pressure diagram, and we divide the trapezoid into two triangles so that we can locate the line of action of F1 and F2, centroids of triangles. So F1 is, this time I use volume of pressure diagram, and the volume of pressure diagram is simply the area of this triangle times width perpendicular to the screen or board, which is 0.8, this one. So F1 therefore is area of triangle 1/2, 9.81 times 1.2, the base here, and the height is this height, which is 1.6, then perpendicular to the board 0.8. So I use volume of pressure diagram. This is the alternate solution, and this is our working equation, by the way. Summation moment about A, the hinge, equals 0. So we have P, same moment arm, 1.6 cosine 30, equals F1, and of course this is 1/3 of 1.6 because this is 1.6 even here. So centroid of triangle is 1.6 over 3, height over 3 of the triangle from the base. So 1.6 over 3, while F2 is 2/3 of 1.6. And 2/3 of 1.6 is 2 times 1.6, 3.2 over 3. So therefore, P times 1.6 cosine 30, summation moment A equals 0, is equal to F1 times moment arm 1.6 over 3 plus F2 moment arm 3.2 over 3. Where F1 is the volume of this pressure diagram, which is area of the triangle times width perpendicular to the screen, which is 0.8. The area of triangle is 1/2 9.81, 1.2 times height 1.6, then perpendicular to the screen 0.8. So 7.534 kilonewtons. Then F2 is area of this triangle, the bigger triangle, 1/2 of 9.81 times 2 times height, which is 1.6 meters. Then perpendicular to the screen, 0.8. So it is 12.557 kilonewtons. If you add 7.534 and 12.557, it should be equal to F in the first solution, where F is 20.09. So just check using your calculator there. Then substitute into this equation, P times 1.6 cosine 30 equals 7.534 times 1.6 over 3 plus 12.557 times 3.2 over 3, and we'll get the same answer as that. So that's it for problem 6. We proceed to the next problem. Each of the 3 gates has a constant width of 2.4, so perpendicular to the screen, 2.4 meters. So that's perpendicular to the paper or screen. Calculate the force P required to maintain each gate in the position shown. Consider the liquid as water, and B is 1.8 meters for this figure here. There are 3 cases. The fourth one is quarter circular, but let's have that later. B is 1.88, H is 2.7 meters, and for the circular gate, R is 1.5 meters. And neglect the weight of the gate in each part. Neglect the weight of the gate in each part. So for the first part, which is this, I'll present 2 solutions. One using the direct formula for F, gamma barred H area, then summation moment about A equals 0. We have reactions at A, but not included in the equation because we sum up moments about A. So, to solve for F, gamma barred H area, specific weight of water 9.1. Barred H is because the projected area is rectangular and the height is 2.7. So barred H is half of 2.7. And the area is the area of this gate, which is inclined. Now, this is 1/3 of length of AB, and 1/3 of HAB is because the length of AB is square root of 1.8 square plus 2.7 square, then divided by 3, that would be 3 square root of 13 over 10 meters. Therefore, the height of AB is multiplied by 3. HAB is just square root of 1.8 square plus 2.7 square, and it is 9 square root of 13 over 10. Again, the length of AB is 9 square root of 13 over 10. Therefore, F is specific weight of water 9.1, barred H 2.7 over 2. The area is the width perpendicular to the screen 2.4 and times height of the rectangular gate. This is the height of the rectangular gate, the height AB, which is 9 square root of 13 over 10. So F is 103.14 kilonewtons. We then sum up moments about A equals 0. So P times 2.7 is equal to F times this moment arm. And this moment arm, 1/3 of HAB, is 3 square root of 13 over 10. Solving for P, P is 41.32 kilonewtons. So that's the first and direct way of solving for P. The other way is, so this is the projected area and the pressure diagram is triangular. So I'll call that FH, and we have FV, weight of liquid above this surface, but we imagine that this is a curved surface, but the principle for FV is it's the same, weight above the surface. So I'll call that FV, which is W, and therefore this is 1/3. The FV passes through the centroid of this triangular area. This is 1/3 of 1.8, so 0.6 meter. And FH is acting 1/3 of 2.7, so that's why it is 0.9. This is the projected area, rectangular, 2.4, which is perpendicular to the screen, by 2.7, the height of the projected height of the gate, or this height given here. So therefore, for FH, it is 9.81, barred H is 2.7 over 2, and the projected area is 2.4 times 2.7. And FH is equal to, it is also equal to the volume of this pressure diagram. The pressure at the bottom is specific weight of water times vertical distance, which is 2.7. So FH is also volume of this pressure diagram, 1/2. Base 9.81 times 2.7, the height is 2.7. Then times width perpendicular to the screen, which is 2.4. So if you compare the values, it's the same, 85.818 kilonewtons. This is gamma barred H times projected area, while this one is the volume of the pressure diagram because the gate is rectangular. So we can apply that. So 85.818 kilonewtons. FV is the weight of liquid above the curve, and the weight is specific weight of water times volume above the plane surface. The volume is area of this triangle times width perpendicular to the screen, 2.4 again. So the area is 1/2, base 1.8, height 2.7, and perpendicular to the screen 2.4 times 2.4. So FV, which is specific weight times volume above the gate, is 57.212 kilonewtons. If you check, the resultant is square root of 85.818 square plus 57.212 square, and it should be equal to 103.14. You check that with your calculator. Then summation moment about A equals 0. So P times 2.7, this is point A. We have reactions here but not involved, 0 moment arms, is equal to FH times 0.9 plus FV times 0.6. So this is FH, the moment arm is 0.9, 1/3 of 2.7. And this is FV, 57.212, the moment arm is 0.6. Solving for P, it is equal to the same answer here, 41.32 kilonewtons. Then we proceed analyzing this part. This is a parabola. Therefore, the area here is 2/3 of base 1.8, height 2.7. So for we only have one solution here. We have here the pressure diagram of the projected area, which is triangular. Therefore, FH is the same as FH in this problem here, which is here in the second way of solving it. It may be volume or gamma barred H times projected area, so it is still 85.818 kilonewtons. It is only FV that changes because this time FV is the weight of liquid or water above this curved surface, and because the curve is parabola, the volume is area of parabola times width perpendicular to the screen, which is 2.4. So FH is the same. Then FV, specific weight times volume. Volume, area of parabola, 2/3 base 1.8, height 2.7 given. Then perpendicular to the screen 2.4. So that's the volume. FV is 76.283 kilonewtons. Then we sum up moments about A equals 0. So P times 2.7 equals FH times 0.9, FH times 0.9 plus FV times the location of the centroid of parabola is 3/8 of B, if that is B and this is H, then vertically to the centroid 3/5 of H. So I'll just include the spandrel of parabola. The location of the centroid along the tangent is 3/4 of B, and perpendicular to the tangent to the vertex 3/10 of H. So remember that. And these locations are in statics, derived in statics. Also, you just look at the derivation. Or you can locate that by your own because you are through with integral calculus. It doesn't mean that after integral calculus you forget everything. You cannot become an engineer if you keep on saying that you forget everything after the course. You pass the course, so it means you know topics there. You can locate the centroids. So FV, 3/8 of B, 3/8 of 1.8, that's the moment arm. So plus FV times 3/8 of 1.8. So solving for P is 48.95 kilonewtons. So let's proceed to this gate here. So for this gate, I'll present another two solutions. One is by purely using F equals specific weight barred H area. So the surface is horizontal in this case. Then the distance of the centroid is here. So barred H is 2.7. The distance from liquid surface to the centroid is 2.7. And for F2, the distance is, we don't solve for E anymore because the liquid surface is flush with the top gate. Or you may use the pressure diagram. So this is 1/3 of 2.7.9. So summation moment about A equals 0, P times 2.7 equals F1, this vertical force here, times 0.9, where 0.9 is half of 1.8. The centroid and center pressure coincide, remember. So this is half of 1.8, so 0.9, plus F2, this horizontal force, times 0.9 also. So this is the first way. So F1 is equal to specific weight. Barred H is 2.7 because the centroid is here. So distance from water surface is 2.7. And the area is the area of this surface, which is 1.8, then perpendicular to the screen, 2.4. So which is this, so that you can imagine. So that's 1.8, that's 2.4. F1 acts through the centroid and the center of pressure also. Center of pressure and centroid coincide. So F1 is 114.42 kilonewtons. F2 is specific weight. Barred H is 1.35. 1.35 is half of 2.7. Then the area of this vertical plane surface is perpendicular to the screen 2.4. The height is 2.7. So 85.818 kilonewtons, which is FH in the preceding problem. So substitute here, P times 2.7 equals F1 114.42 times 0.9 plus F2 85.818 times 0.9. P therefore is 66.75 kilonewtons. Then for the second way, using weight for F1, because we have here the weight and volume for F2, volume of pressure diagram. So weight 1 is simply the weight of water above this horizontal surface, horizontal plane surface. So weight 1 is specific weight times volume. This is the working equation, P times summation moment A, P times 2.7 equals weight 1 times 0.9 plus F2 times 0.9. So it's the same. So weight 1 is specific weight times volume, specific weight of water 9.81. The volume is area of this rectangle, which is 1.8 by 2.7 times width perpendicular to the screen 2.4. Which is this 1.8 times 2.7 times 2.4. So 114.42, the same. Then F2 is equal to volume of pressure diagram, and 9.81 times volume of pressure diagram. So 9.81 times volume of pressure diagram, 1/2, times 9.81 times 2.7 times 2.7. So this area of triangle here times width perpendicular to the board 2.4. So F2 is 85.818 kilonewtons, which is the same. So one half, it is just what this is volume of pressure diagram. 1/2 9.81 times 2.7, the base, the height is 2.7, and times 2.4 perpendicular to the screen. So it's the same, 81.818 kilonewtons. So therefore, P is 66.75 kilonewtons because we have the same value of F1 and W1, same moment arm. F2, we have the same value. So 66.75 kilonewtons. Then for the circular part, R is 1.5. I'll present two solutions here. So summation moment about A equals 0. P times R, which is 1.5 meters, is equal to F1 times this distance here, 0.5. 0.5 is 1/3 of 1.5 because the pressure diagram is like this, triangular. So 0.5. Then plus FV times this distance. This distance in general is 4R, 4 times 1.5 over 3 pi. If we simplify that, that's 2 over pi. So FB times 2 over pi. F1 is specific weight, barred H, area, projected area. Specific weight of water 9.81, barred H is half of 1.5. This is the projected area, which is rectangular. Therefore, barred H distance from water surface to centroid of projected area, half of 1.5. Then the area, projected area, 2.4 times 1.5. So 26.487 kilonewtons. FV is the weight of water above this curved surface, and the weight of water is specific weight of water times volume. The volume is area of quarter circle times width perpendicular to the screen, which is 2.4. So 9.81 times area of quarter circle, pi over 4 radius square, then width perpendicular to the screen, 2.4. So 41.606 kilonewtons. Substitute here in our working equation, P times 1.5 equals F1 26.487 times 0.5 plus 41.606 times 2 over pi. So P is 26.49 kilonewtons. So this is the second way. The second way is since F, the resultant, passes through the center of this circular arc, and these are the components, F1 and FV. So we can move F here and resolve F into its components, F1 and FB. So we don't mind this FB here and F1 here. We just consider F1 acting at this point and FB acting at this point. Now, Since the moment of the resultant force is equal to the sum of the moments of its components, therefore Fv passes through A, only F1 will have moment about A. So if we sum up moment about A equals 0, the equation would now be P times R equals F1 times R. Fb passes through A, so we transfer F1 and Fb by principle of transmissibility of a force at this point here, because F1 and Fb may be replaced by the resultant force F, and F passes through the center of this circular arc. So that's the principle in statics. If you stick to the first solution, then you may. But the second solution is simpler. So P times R equals F1 times R, cancel R, so P is just F1. But F1 is 26.487 to 4 significant figures, 26.49 kilonewtons, which is the same as that. So that's it, because the video is now long.